I'd like to invite David on the floor.
Just a minute.
Yeah. Was going to talk about efficient planning and for robots.
Thank you, Raj. Hi, everyone. So yeah, my name is David Rodriguez. You probably have seen me here all morning, struggling with the computers and the presentations and so on. I'm a research scientist at the Advanced Quantum Architecture Lab, and I'm going to introduce you to what I found to be a common thread across the research that I've been doing over the past 5 years or so. And that has been trying to find answers to this particular question of how we can actually make a significant impact on the efficiency of exploration. So I understand that there is two words there that require definition, one being significant and the other one being efficiency. So I'm going to try to do that. Keep in mind that I'm a mechanical engineer by background. So whatever I say from now on is going to be a flawed definition of what efficiency and significant means to me, since I started early on working on off-road locomotion, is going to be distance, right? So when I talk about significant impact on efficiency, I'm talking about increasing into orders of magnitude the amount of distance that we cover per mission. And for those of you that aren't familiar with space exploration, we don't go very far, right? But at the same time, doubling at least the amount of meters that we can actually explore per 100K invested. And this is particularly interesting for lunar missions. So just to give you a reference of what that means, Apollo and Lunokhod missions, that ratio was under 1, so we're 0.7 or so. The upcoming NASA's Viper mission, if everything goes according to plan, will be around 3 meters per 100K invested based on public numbers, right? So the idea would be to at least double that. So with this in mind, again, I'm going to introduce you to what I've done, the results that we found, and some of the new things that I'm trying to do now to try to find, again, answers to this particular question. And I want to start with, well, this was also presented early on, so I thought I had removed this slide, but very quickly, I think all of you will know why is answering that question so challenging. Of course, in a space, we're very risk averse, everything is very costly, so we double check and triple check everything. So that's one of the reasons why we're so inefficient sometimes doing our exploration. We, of course, don't have access to data sometimes, and the data that we have sometimes isn't that good. So that limits a lot of the efficiency that we can actually bring into the table. Lack of illumination. I haven't seen a lot of talks today mentioning these aspects. So either I have a wrong understanding of the limitations that we have when it comes to south polar regions on the moon. So we have those permanently shadowed regions, transiently shadowed regions. So the sun on the poles of the moon only appears very slightly above the horizons. We have very long-winded shadows that we have to deal with. Navigation systems have a hard time dealing with that. Of course, all the well-known limitations that we have in space, right? Like computation and electric power, communication bandwidth and mass that we have to cope with, and all the other stuff that wants to kill us, right? So that will be very unstructured, heavily cratered and hazardous abundant landscapes, micrometeors that are impacting all the time, and radiation, right? So we have to cope with all of that alongside trying to make our missions more effective. So I'm going to talk about, as I said, what I've been doing. So what I did, what I've been doing, and sort of like what's the plan moving forward. And that's from fast mobility to quantum imaging. Starting with research that I started doing when I was still part of Professor Yoshida's lab at the Tohoku University, and that's fast off-road mobility. So as I said, we started looking at this aspect from the point of view of locomotion, and I promise I will not go deep into the terramechanical aspects. I know this is a multi-robot workshop, but it's worth also mentioning that when at least I talk about fast mobility, those are velocities that are over or close to 1 meter per second. Again, for those of you that maybe not be that familiar with the space speeds for ground robotics, current rovers only move at speeds that approach, a couple of centimeters per second at best. So that's already a 2 orders of magnitude improvement of the current speeds that we often consider. So what's the idea behind, or what was the idea behind this project is, one, trying to understand what happens when we have like wheel-soul interactions at faster speeds, because we didn't know. So when we have, different types of wheels interacting with different types of lunar simulants, and trying to model that interaction so that we can have better simulations, better predictive models of what the performance may be. And then, of course, with the results of those experiments and those simulations, trying to design better systems, right? So I have a video of some of the activities that we did. It's a very epic music, so apologize for that. I'll try to talk over the video though. So this is some experiments that we did, again, when I was part of Tohoku University with the help of ESA and DLR. Actually, those were conducted at the Terramechanics lab at DLR, so I'm very grateful for that. It was actually one of the few places where we could do these tests, because they have a little sandbox that is large enough to achieve 1 meter per second speeds and have like steady state data that we can actually use. It was a lot of dealing with dust. Okay, no epic music. So there we go. So one of the reasons that was also very interesting to do experiments here is because, unlike normal single wheel test beds, if you are familiar with those, we had a hook arm that was acting as a kind of like a guiding mechanism for the wheel. So the wheel was motorized. It had its own actuation system. Everything was automated, which was great, because often this is not what we deal with. So we could, rake the sand, prepare the sand after, and so before and after every experiment. You'll see some. So this is I think it's a slow motion video of if it plays. If not, I'll talk over it. But it's a slow motion video. So we did. I mean, imagine I spent a month here, so I did every single experiment I could think of. So we tried different wheels, different soils, and also different conditions. So we tested also highly dynamic situations with wheels accelerating from 0 to 1 meter per second. You can see the different types of soil. So on the left side, you have a calcite-based silty soil. That's similar to what we may expect on the moon. So highly compacted, very fine-grained soil. It's almost like walking on flour, which is very challenging. And this is just something that I like, that I recorded when I was leaving. So we use fluid dissection to kind of like mix the sand. So this is pressure air, air been just blown from the bottom of the sandbox to just mix everything, which was pretty cool. And I had a high-speed camera, so I wanted to use it for something. Just very quickly, what is it that we found? Again, this is very extensive. I'll suggest, if you're interested, to look at the paper. You'll see lots of data there. But basically what we found is that overall, across the experiments that we did, up to speeds of about 20 centimeters per second, we didn't find any meaningful degradation on performance. So you could, speed up your rovers up to 20 centimeters per second, and it will be pretty much the same in terms of tractive efficiency and overall terramechanical performance. Beyond that, things start to be a lot more tricky, if I may say so. So sand is a very complex component to deal with, because their apparent properties changes based on the strain of the formation, based on how you impact the sand. So the moment you start going on the rate of that, particularly the rate, not just the absolute value. So the moment you start exciting sand at higher velocities, it stops behaving a lot more like a solid and starts behaving a lot more like a liquid. And then weird things start to happen. So you have higher sinkages, and there's when we started to think about new designs for wheels and suspension systems and so on. Again, I'll recommend you to check the paper or come to me. I'll explain you more about this. We also tested different types of wheels with that, and flexible wheels across the board perform a lot better, as you may imagine, but also at higher speeds. And yeah, so that's pretty much what we found. So then the next obvious step was to look at the aspect of navigation, right? Okay, we know how to make our mechanical system somewhat more optimized for faster speeds, but it doesn't matter if we have a very fast blind robot, right? So we wanted to look at the aspect of navigation. How can we actually increase the efficiency of our DNC architectures? And here's where the subject that I'm working on right now of quantum imaging came about. And this is pretty much the question that I've been receiving for the past 4 days every time I mention this, which is Q what? I know it's like, well, so let me explain it very briefly. There's probably people in the room that knows a lot more about quantum than I do, because I just started early this year. So I joined Eduardo Sarvon's lab at EPFL early this year, and I'm getting just familiar with what the technology can actually do, and I'm going to tell you pretty much what I know about it. So just to get everyone on the same page, Quantum imaging basically means using, so it's imaging technology based on quantum principles. And there are plenty of quantum principles in here. I'm going to focus primarily on one, which is the quantization of energy. And what this means in essence is that if we get any normal camera based on CMOS sensor, right? The principle, the functional principle of that camera would be there is a gate, there's a span of time at which that camera is basically accumulating light. And then based on that accumulation of light, you have an electrical output that then you read out as an image. So the sensors that I'm starting to use now, what we call single photon avalanche diode sensors or photodetectors, instead of accumulating light, they will give you an electrical output every time there is a photon impacting each of the pixels. So what this means is that in theory, there is no noise. So there's no time for noise to come in. We can have readouts at speeds that go up to 100,000. 100,000 frames per second. And we have a lot higher high dynamic range compared to normal cameras. And I would mention that CMOS cameras are already getting very advanced. And I'll mention something that makes using quantum sensors or quantum imaging, in particular the SPAT sensors, very interesting for our particular applications. So this is the camera that we're working on. Right now it's in a prototype proof of concept state. It's called MEGA-X. It's a 1 megapixel SPAT camera. You can get frames at speeds up to 24 kiloframes per second. That's also, I didn't mention this, but that's basically binary frames. So that's ones and zeros. Either a photon impacts or it doesn't impact on each of the pixels, and that's what we get. Then we can batch those images and get, whatever size of image you need, 8-bit, 16-bit, 12-bit, whatever you need. So now we're working on bringing this camera out of the lab and into the robots that I'm coming in to this new lab. But basically you can do things like that, like this, right? So you would have, I mentioned high dynamic range. So this is some of the things that you can do. We have on the top is a single exposed image and the bottom is the dual exposed image. And another particular interesting application is that if you pair these sensors with an active laser source, then you have a flash LiDAR and you can use it as such, which is pretty cool. And then you can do depth imaging as well. Also, I should say that the temporal resolution of these cameras is also very, very tiny. And that's why most of the time these type of sensors have been used for astronomical applications. So how can these be used for some of the problems that we mentioned here today? I'm just going to mention a few. This is work that has been done primarily by some colleagues at my group and also Mohit Gupta's group in University of Wisconsin-Madison. So the papers are there. This is not my own work. I'm just going to showcase. It's a very interesting paper because they basically showcase the potential that these new sensors can have in some of these applications that we mentioned here. So as I said, we're capable of doing very fast imaging with complex lighting conditions, and then becomes very interesting because of what I mentioned before of like going to the moon, to the south pole of the moon and trying to explore there, or getting into a cave with no natural light and trying to explore that. So you have some examples of fast object and feature tracking using night vision cameras, thermal cameras, and also our SPATs. I believe the set of images on the right side, the object tracking was actually done by hand, but on the left side, I think it's YOLO V3, the one that they use for object and feature tracking. You can also do, as I said, very high dynamic range. And this is what I just mentioned of SPATs start to become very interesting when you start to apply it with something that's called quanta burst. So you're probably all familiar with burst photography. I think some phones also have it. I use a very old phone, so I don't know. But I've been told that some phones already have burst photography. And when you start to pair, so I said that we can take images up to 100,000 frames per second, those binary images, those, there is or there isn't light. The interesting thing is that when you start to batch those images and through these new algorithms called quanta burst photography algorithms, you start to have images that are denoised, so there's no blur. You can take those images at very low light. And if we manage to optimize those algorithms so that we can start to run them real time on chip, then the whole branch of robotic applications opens up for us. This is just some of the details of how this quanta burst photography works. Again, this is work being done by Mohit Gupta's group, Wisconsin-Madison. But if you want to learn a bit more about that, the papers are there, or just come talk to me. I'll explain you whatever I know about it later on. So then I just want to wrap up with maybe the reason why I'm also talking here, apart from organizing this whole thing, is because we started doing some work, and this is pre-phase A for those familiar with the space systems engineering and so on, project on a potential lunar reconnaissance drone. And the objective here was to design. So we basically thought about how terrestrial drones were being used. And basically we tried to transfer that use case into planetary exploration, in particular for this type of airbots, right? So we wanted to have a fully autonomous, lightweight, compact and reusable lunar drone, in particular for the high resolution mapping of those regions of which we don't have good data. That would be permanently shadowed regions, that would be lunar skylights, where the highest resolution data that we have, honestly, is just about, I think the best we have currently, based on ShadowCam, which is on board the Korean orbiter, is 1.7 meters per pixel. So the idea is to go way below that. So we have at least resolutions that are half of a characteristic length of the robotic systems that we are deploying. So that will be centimeters per pixel. Right? So this is the first ConOps that we came up with, right? So you will approach with your rover, you will open the hatch, very Hollywood-like. So you will open the hatch, you will deploy your drone, you will map the area at high resolution, and then you can come in safely with the rover later. The problem that this has is that it was going to be very hard to find rover operators that would allow us to fire 4 rocket engines on top of their own rovers. So in the end, we decided to change this, and the current concept of operations that we presented actually has a trailer. So what we call the service station, which is that thing on top of the rover, which has refueling tanks, batteries to recharge the drone, is now placed on a trailer. So then we can adapt it to any rover, any ground vehicle that it's operating on the surface, right? Again, I don't have a ton of time, but I'm going to give you just some basics of what this looks like. We're working on a paper. I think there is some details there that will be submitted soon. And so if you're interested, just again, drop me an email or talk to me. I'll give you more details about it. So in the end, this drone is going to be not smart at all. So basically what it would do is a predefined trajectory that is comprised of a semi-ballistic takeoff and landing. That's a 5-meter vertical takeoff, followed by a ballistic ascent or climb. That's just to optimize fuel consumption. And then it will follow a straight, constant above ground level flight profile coming back to the same location where it took off. That's the service station. There's a reason why we're not landing on the moon, on the surface of the moon, that is. And if I have time, I'll mention it. I'll mention why. So and here you can also see the bottom graph is just fuel consumption over time. So we can do with the current system, we can do about 11 flights. Each flight has about 800 meters of flight coverage. And we do that in about 140 seconds. I think we consume a little less than 2 kilograms per flight. I didn't mention the design, but I'll mention it now. So here you can see on the right side, you have the design of the service station, so the trailer. The whole system is designed so that it weighs less than 100 kilograms. The drone, without the kind of like covering panels, the concept design of the drone, that is, you have it on the left side. And we use 4 monopropellant thrusters initially. So again, I said this is a preliminary design, conceptual design, right? So we try to base all of the components that you see there on off-the-shelf components. So we use hydrazine-based monopropellant thrusters to baseline the design. The idea, of course, will be to move towards more sustainable and reusable hydrogen peroxide type of engines as the design evolves. But that's what we're using right now. And then, of course, as the payload, we use one of our cameras. For the baseline of the design, we use a flash LiDAR, but the idea would be to pair it with the Mega X that you saw before, and that's pretty much it. And I think this covers everything that was planned for my presentation. Thanks a lot.
Yeah, thank you, David. Nice presentation, and thanks for touching upon all the aspects of your research. Yeah, questions for David in the realm of locomotion, quantum, other technologies that you mentioned. Yeah.
Yeah, thank you. I'm quite interested regarding the quantum imaging. For today, we are talking about space robotics. I'm wondering, do you have a plan how we can use quantum imaging for space applications?
Yeah, so I'm really sorry I had to kind of rush through the whole presentation, but so there is 2 main applications we're looking at, and both of them combine two characteristics that I think make quantum imaging or the sensors that we use particularly useful for, and that is highly dynamic applications. So when you have either yourself or the target is moving fast, and challenging illumination conditions, right? So if we look at the moon, light there doesn't scatter. So things are either very, very bright or very, very dark. Same happens in orbit. So if you need to do things like orbital debris removal, right, which has to be 100% automated. One of the pain points of that operation is the vision-based navigation, which has to be autonomous. And in particular, the lighting conditions. So it's the 6D post-estimation. You can use this type of systems, which can also do event-based mapping because of the high frame rate. With the benefit that when there's no motion, you can actually also take still images. Orbital in-orbit servicing automated applications would be one. And of course, exploration of challenging areas like shadowed regions, skylights where there is no natural illumination. With this type of cameras, we're doing tests right now at extremely low light. So we're going at 20 and below milliluxes. So we may have here about like 500, 600 luxes, more or less. Usually normal cameras, although again, the technology has improved a lot. They tend to go about tens of luxes, and below that they start to have challenges with the quality of the output images. So those are the two main applications, right? So when you combine, again, just to summarize, so like high speed with extreme low light, or even just challenging conditions of very bright, very dark combined in the scene, there is where I think these sensors could really shine.
Thank you. Any other question for David? If not, please join me in thanking David for his presentation.
Thanks a lot.